The search for extraterrestrial intelligence, SETI, is all about finding alien civilizations, and the bigger they are, the easier they should be to spot, and there's few things a mega-civilization might build bigger than a Dyson Sphere. One of the biggest topics this channel covers is the idea of massive space habitats, and whole clouds of trillions of them being built around stars, conglomerations referred to as Dyson Sphere or Dyson Swarms. And another is the Fermi paradox, the big question of where all the aliens are in a universe so old and vast that it seems impossible that other civilizations would not have arisen yet. Today we'll be discussing the connection between these concepts and if such Dyson swarms exist, how they would be visible to us if they do, and why they might not be visible, get hidden, or even not be built in favor of other approaches by alien civilizations. All the way back in the show's first official Season 1 episode, The Fermi Paradox and the Dyson Dilemma, we discussed how Dyson swarms should be an inevitable project of any spacefaring civilization, and in many ways that discussion is the reason this show exists. We spend a lot of time talking about what big, high-tech civilizations might do, and why the apparent absence of these sorts of structures, such bright and loud displays of their existence, would seem to indicate there are no loud alien civilizations, or perhaps even any alien civilizations at all. There are a lot of reasons to question that claim, and we have discussed many of them over the years. 5 recurring ones I want to address today are: 1. Could we actually see a Dyson Sphere? 2. Couldn't such a powerful civilization hide their Dyson Sphere from us? 3. Wouldn't a better power supply than fusion eliminate the need for a Dyson Sphere? 4. Where should we be hunting for Dyson Spheres or groups of them? And 5. What about all those voids, dark matter and stuff like that? Couldn't those be Dyson Spheres? I suppose the first thing to do is to answer what a Dyson Sphere or swarm actually is. This naturally has to be a vague answer since it's really just an assumption that since planets generally only get a tiny fraction of the light their sun emits, not even a billionth in Earth's case, that civilizations seek to find a way to capture and use more of that energy. While the basic concept is named for Freeman Dyson, it is at least as old as Olaf Stapledon's 1937 novel, Star Maker, and the usual notion is that this is a vast collection of physically disconnected artifacts using that power, much as buildings, plants, and farms make use of sunlight and land here on Earth. But the notion of a big hollow spherical shell people lived on, like an immense inverted planet, is what got stuck in the public imagination, so we tend to use the term Dyson Swarm to emphasize that it isn't a big hollow shell around a star. Usually anyway, as we've discussed elsewhere, the big hollow sphere option is doable too. Either way, this is where the Kardashev scale pops in, as astronomer Nikolai Kardashev suggests a few levels of astronomically detectable alien civilizations. One is for those who have significantly altered the spectrum of their planet, presumably peaking out at total usage of their sunlight and its emissions as thermal infrared light at the frequency associated to the temperature of their planet and life forms. The second level is just a nod to the idea of a Dyson swarm, that they will have significantly changed the spectrum of their home star, their sun, by surrounding it with lots of power collectors and the equipment using them. And again, the notion is that they will eventually completely encompass their star, though in neither case do we just take that for granted, as we'll discuss in a moment. Level 3 is just an extension of this notion to assume they will eventually do this to every star in the galaxy, and that's as far as the Kardashev scale goes, though we did decide back in our Grabby Aliens episode that any civilization that did that to an entire supercluster or more of galaxies would be Kardashev 4, and anyone doing that to the whole observable universe or a Hubble volume would be Kardashev 5. Our interest today though is Kardashev 2 or K2 civilizations, ones with a Dyson, and we need to start by emphasizing that detecting these does not pivot on them being fully encapsulated stars. Stars have certain characteristic frequencies that they emit based mostly on their mass and age, but lots of anomalies can creep in. For instance, if a star was being orbited by 2 planets that hammered into each other, you would have a long period of time in which a big dust and debris cloud orbited that star, absorbing way more sunlight than those planets used to emit, and re-emitting at the frequency and wavelength corresponding to their temperature. that's going to be a big smear of infrared along with reflected light. Would we confuse that with a Dyson? Well, maybe. This was one of the preferred solutions for Tabby's star, along with options like a swarm of disintegrating comets. Something like that is not stable. The fragments will start reforming into bigger objects, and the solar wind will blow the dust away over time too till it clears out. Given time, we would see that effect, but we are talking centuries, not days, to notice that difference. Still, that's not the only aspect of Dyson detection, because such a dust cloud would reflect lots of normal sunlight away rather than absorb it all, and a Dyson swarm might reflect a lot of sunlight too, but that's not optimal, and more to the point, it would match up with the characteristic absorption and transmission rates we would expect for dust made mostly the same elements in the same composition that star itself and its neighbors had. A trillion solar panels absorbing sunlight and reflecting some away and emitting some as infrared just does not have the same spectrum a cloud of dirt, ice, and rock has. Nor are they likely to be distributed the same way in terms of distance and density. Other natural phenomena that we might confuse with Dyson swarms are distinguishable this way too, and the simple answer is that we truly could be fooled fairly easily nowadays, but not for long or with superior gear and observational time. Fundamentally, science is about hunting for patterns and anomalies, then trying to determine what natural or artificial process is causing them and how. Until you've nailed that down to a tiny margin of error, you never stop trying to account for an anomaly, and it is very unlikely anything purpose-built is going to have identical characteristics to something natural. A leaf might resemble a solar panel, but not on inspection, so the object will stick out the more you look at it. The exception to that, of course, is if the purpose was stealth. Aliens wouldn't expect to be able to hide this way either, as they presumably are only interested in hiding from possible threats, and they will assume anyone bigger and older than them probably saw their planet's atmospheric biosignatures even before they started transmitting radio waves. They're going to assume long-range interest in them too, alien astronomers noticing the interesting but probably natural dust cloud, and checking on it regularly as time passes and their models improve, and wondering why it wasn't matching expected decay rates. This also goes to our general notion that intelligence recognizes intelligence, and that artificial never looks natural without an effort. Nobody is accidentally hiding, and while an old and weathered flint arrowhead by itself might make some wonder if it was natural or artificial, someone's buried house or garage full of various tools and appliances is not going to have anyone wondering if it was natural or not. The Giant's Causeway might look like a road on first glance, but not for long, and is also missing secondary indicators like road signs along the way or signs of being carved by tools. So how far away could we see a Dyson Sphere right now? That is also a tricky question because it depends on what kind of star it is to begin with. A supergiant that someone has built a vast star-lifting array around might be 1,000,000 times brighter than our own sun, while the vast majority of stars are only a few percent as bright as our sun or less. By default, we tend to look for copies of our sun and think in terms of that, and there's some justification in this case. See, the crux of the hunt for Dyson Spheres isn't really about finding just one. The assumption is that anyone who builds one will build more and nearby. We wouldn't expect them to stop at their home system, and we would not expect their home system to be some enormous supergiant whose lifespan is barely 1,000,000 years. That's not really a conducive spot for life to evolve. Alternatively, we have no strong reason to think smaller red dwarf stars would be inhospitable to life, and they live far longer than even our sun. So if you're hunting for a civilization that built multiple Dysons, checking out those bigger stars makes sense, as they are visible far further away and would be prime targets for various stellar engines. Those come in a lot of types too, from simple power collectors to literal star drives designed to move that star like a big spaceship, from massive habitat cylinders mimicking the conditions of their homeworld, only 1,000,000,000 times more numerous, to ones designed to run enormous computers on which artificial intelligence or uploaded minds and entire simulated universes could exist. These change light spectrums, and indeed they might change a smaller star's spectrum to match their home star by the technique of star boosting, which should also be rather noticeable astronomically. And they are not limited to harvesting sunlight. They can perpetually refuel their star with hydrogen brought from gas giants from afar, while pumping all those heavier elements out of it via star lifting, reaping thousands of planets worth of heavier elements. They can power massive telescopes and transmitters, They can grow food to feed quintillions. They can run massive supercolliders for science or alchemy. They can build armadas of spaceships to colonize the galaxy and push them up to interstellar speeds with massive beams of matter or light. Needless to say, when folks ask why you or some alien civilization would want to build a Dyson Sphere, the reply is, why wouldn't you? Because there's so much you could do with one, or many. That's why we can really only see it not being done, either because a civilization went extinct or found something better, and we'll return to those points in a while. As to if you could build one, see our Dyson Spheres episode for the various options in greater detail, but the answer is yes. Even a single larger asteroid would let you produce enough thin metal foil and solar collectors to englobe the sun. Other applications do take a lot more mass, but once you get to this stage, you now have all the energy you need to disassemble whole planets if you need to. Jupiter on its own masses as much as every other planet, moon, and asteroid in our solar system combined, and has a metal-rich core far larger than Earth, and the Sun itself contains 1,000 times that. Some stars will have more, and indeed Jupiter is not particularly large or noteworthy as planets go, it's just our local behemoth. Bigger stars have more sunlight and need more mass to englobe, but also will tend to have far more mass on hand to build with, and small red dwarfs only 0.5% the brightness of our Sun would still have the power to light 10 million Earths, and proportionally far more metal on hand per unit of sunlight they emit, as such a star, 0.5% as bright as our Sun, probably masses fully a quarter of what our Sun does, so effectively 50 times the mass per watt of light to build with. This does not really answer the question of how far we could see one, and the answer is how far off could we see that star normally, and adjusting for how we could see its change in peak spectrum. Sunlight gets absorbed, but only temporarily. Things emit thermal radiation based on their size and temperature, and as they grow hotter they emit exponentially more. Some object twice as hot would emit 2 to the 4th or 16 times the light. Something 10 times as hot, 10 to the 4th or 10,000 times as bright. Our Sun actually emits thermal radiation that we call sunlight. The actual power is all derived from gamma rays and fusion deep in the core. So things absorbing light grow warmer until they reach an equilibrium where they emit as much as they get, just at a different frequency. We usually assume Dysons are built at about our planet's temperature, a 1/20th of the Sun's surface temperature in Kelvin, which means needing 20 to the 4th or 160,000 times as much surface area as the Sun. The square root of that, or 10 to the 20, or 400 times the radius of the Sun. This is actually decently wider than Earth's own orbital distance from the Sun, as Earth reflects a lot of sunlight unused and has a night side. A highly reflective object can be closer to a star without being as hot. So could a thin, long object like an O'Neill cylinder that had its axis pointing towards its Sun for a low cross-section. We might expect a habitat devoted to tending a large collection of power collectors near a star to take this attitude, but there's no requirement a Dyson be that large. Indeed, a power collector probably would be as small as you would get it without melting the device, and for that matter you might manage a star whose spectrum you didn't like, or which was prone to flares, by englobing in something like a tungsten sphere that would emit a nice steady light just like a classic incandescent bulb, which might be preferable to some white-hot Type A star blasting the area with vast amounts of ultraviolet light. This is how you deal with hotter stars than our Sun to cool their light. Star boosting again is how you deal with cooler ones. Build a tungsten globe around our Sun at twice the diameter the Sun's photosphere is, and that is a Dyson sphere that will quickly rise to that equilibrium temperature and give off the exact same amount of light the Sun does, but since it's twice as wide and thus has 4 times the surface area, it will reach an equilibrium at a temperature corresponding to a surface a quarter as bright per unit. That would be about 4100 Kelvin, slightly hotter than the brightest red dwarfs in the low K-type orange dwarf star range, like 61 Cygni b, a K5 main sequence star, except that it would mysteriously look twice as wide as our own Sun, while 61 Cygni b and other main sequence stars of its temperature are just over half as wide as our Sun. So again effective, but not covert. Now that's okay. If we saw that and at a distance and a quick glance, we would probably assume it was a star leaving the main sequence, which gets brighter and wider as they expand to be subgiants and eventually supergiants. Except we could then compare it to other examples and measure its mass and realize it was off. There's not that right absorption and emission spectra for elements like sodium or nitrogen that would be in many a star's atmosphere. Alternatively, another Dyson, a partial one in terms of habitats, might show the sorts of emissions and absorption spectra we would expect from a life-bearing planet, a biosignature like lots of oxygen and some carbon dioxide, only at thousands or millions of times what a normal planet might show. Of course, we determine what's normal by observation, so it's always possible some type of star we take for granted as natural is actually the baseline model for stellar engines that basically every civilization builds, so they're scattered all over the universe at a fairly normal density, and we tricked ourselves into thinking it was natural. That doesn't work either though. Generally, if something is an artificial construct, we would expect them to be regularly produced until candidate systems ran out, and more importantly, we would expect to see them be far rarer in the distant past. And astronomy is history. We can see 10 billion years back to when even the oldest stars were younger than ours was when life crawled out of the sea. We would expect an artifact to grow rarer the further out we peered in space, since we see back in time when we do that, and we call this T, or the time elapse argument of the Fermi paradox, that any phenomena suspected of being an artificial construct should grow rarer the further away or back in time we look. If it isn't, then it's probably natural, and quasars are an example of that. We wondered if they might be alien signals originally. Indeed, realizing they were brighter objects than not just stars, but entire galaxies, didn't make us think they had to be natural either. We just wondered if they might be megadysons, Kardashev 3 civilizations. But as we mapped them out and checked the distance over the decades, we found it was very rare to find any within a couple billion light years, and they were most common about 10 billion light years away or 10 billion years ago. That needs a caveat though. We can see quasars that far away because they are insanely bright, but we can't distinguish individual stars that far off very well. We generally see even fairly close galaxies in our own supercluster as fuzzy dots even through powerful telescopes, and that's not really looking far enough back in time to apply T. Hubble really extended that argument, and James Webb even further, with the current record holder for most distant star being Earendel, whose light took 12.9 billion years to reach us. And yes, for Tolkien fans, it is named for the father of Elrond and the first king of the Númenóreans, and Aragorn's 62 times great-grandfather, the one from the Silmarillion who the Valar set to sailing the skies with a Silmaril as a star in the sky. Since I am a fan of the Lord of the Rings, I think this is a very proper name, along with a huge chunk of Pluto being named Mordor now, as opposed to always mining ever more obscure bits of human mythology, but I digress. We don't really have vast archives of individual stars and distant superclusters to check for what's normal, especially normal modern stars. Webb is specifically designed for seeing early galaxies, and some 13 billion-year-old star visible that far off is probably not a good baseline for the kind life-bearing planets would have developed by. So, we always need this context on detection that we can only talk about lone Dysons in our own galaxy and maybe its nearer neighbors, Andromeda, Triangulum, and the Council of Giants ringing us. Our assumptions for looking beyond are the idea of detecting truly giant examples that might rival a quasar or Birch planet, or large groupings of Dysons in a galaxy showing us a dark sphere in the visible range, but emitting much light in the infrared. To restate, we could easily miss a Dyson, particularly a partial Dyson, even in our own galactic backyard, even if we were looking right at it, but that window is closing rapidly as we build up our catalog and observational abilities and analytical toolbox. We simply assume folks would keep building these things and they would give off lots of other artificial telltales too, when inspected, much as a city will not be confused with a natural hill or rock outcropping from the million different signs of artifice present, from the big neon sign saying welcome to the text and logo covered trash flowing down the river from it. Same with a Dyson Sphere, which has the power to make welcome signs seem galaxies away, but they also produce the trash of waste heat and other telltales, and if we missed one now, we won't for long, and it wouldn't take much to raise our curiosity so that we stared at it and saw the abnormalities for signs of artifice, not nature. Which takes us to question 2. Could not such a powerful civilization hide their Dyson Sphere from us? This one is even harder to answer since you can't just say no when talking about a civilization older and more powerful than your own. We don't know what they can or cannot do, but we've never learned how to break the rules of the universe in centuries of studying them, and there's no real reason to assume they have, or they found some vast supply of cheat codes. We will discuss that option in a moment, but let's assume for the moment that they cannot break the rules. In this case, we can then say the answer is no, because this question is usually asking why they can't stop themselves from emitting any radiation, and the problem there is that you could, very briefly, then you'd burn up from all that absorbed heat. Something we tend not to think about is that the average temperature of our own solar system is hotter than the surface of our sun. After all, virtually all the solar system's mass is in the sun, whose core is far hotter, and even most of Earth is murderously hot, since only the upper crust is survivable, and the mantle and core are both hotter than the surface of some dimmer suns. Only that tiny fraction of the solar system's mass that makes up the smaller dwarf planets, asteroids, and moons is cooler than Earth's surface. It would take very little sunlight focused on them to warm them all up, too. Key notion here is that there are not vast reservoirs of core out there to be storing energy up in as heat. Earth is not a rare warm place with most things being cold as Pluto. Conglomerations of mass tend to be hot. Not surprising either, the laws of thermodynamics tell us all energy eventually ends up as heat, which includes chunks of matter falling in on each other under gravity to form a planet or moon or stars. Usually, you're lucky if you can use a packet of energy to get some work done without at least half of it ending up as heat. But even some 99.9% efficient process just means you leak your energy into heat slower with each use. It doesn't really change that it all ends up that way and has to be radiated away if you don't want to turn into a crisp. If you have technology that ignores the laws of thermodynamics, then yes, you can shield yourself from emitting waste heat. Maybe. It still wouldn't seem likely you could hide yourself completely with no leaks, but this works well enough for two big reasons. First, you don't really need a Dyson Sphere at that point. You can't just keep recycling your power supply, and there's less need to venture into the emptiness of interstellar space for more resources around other stars. We have an effective infinite pool of them, depending on how and how well your thermodynamics breaking clock tech works, of course. Second, and just as importantly, these folks are not hiding themselves, they're just being efficient, and that makes a big difference. We'll come back to the special case of dumping the harvested energy or heat into black holes in a bit, but by and large, any effort to hide a Dyson, where that's the intent, is basically futile and they know it. It takes vast efforts and energies to hide yourself, and for no reason since it doesn't work. So you've blacked out your civilization at an enormous expense. Great! And any older civilization probably was sitting there watching you, wondering why you thought hiding now was going to erase all the evidence of your existence already meandering out in the galaxy at light speed from when you invented radio, or when your distant ancestors evolved photosynthesis and other atmospheric biosignatures were present. Plus, maybe you beat your light emissions, but what happened to your gravity? You suddenly shut that off? Big old mega civilizations with huge telescopes and computers not gonna notice your star disappearing, along with all its gravitational influence on neighboring bodies? You presumably are afraid of big dogs who could hurt you, with big fleets of star destroyers, not planets and civilizations like ours currently is. So hiding from us doesn't achieve much, and those bigger, older alien civilizations are not just limited to telescopes. If you're afraid they have fleets of battleships at their disposal, then you maybe take for granted that they have vastly more cheap and effective probes to send out for periodic flybys of places. Plus, they probably have this same technology you do. Otherwise, they wouldn't really be a threat to you given it's essentially unlimited energy to run your factories and guns and spaceships, which means they probably know the little giveaway telltales that let them detect a cloaked ship or outpost, let alone an entire star. But if you have this technology, it works well enough for the Fermi paradox because you're not actually hiding, not suffering a cost. You just have a very efficient engine that is so good it doesn't make a lot of grinding and noise and fumes, and so people don't really see or hear it. Of course, you probably put running lights and sirens on it so they can. Remember, this is a civilization with vast energy supplies and who do not feel expansionist, which generally implies they don't view it as advantageous, which, since they're intelligent, presumably means it actually is not, and that they are not worried about invaders. So they hang bright neon signs up to let people know they're there in case they have anything interesting to offer. To touch on the black hole case and segue into our third question, wouldn't a better power supply than fusion eliminate the need for a Dyson sphere? Since energy equals mass, one thing you might be able to do with all the power of a star at your fingertips is focus a lot of its energy into one single place and moment, and create what we call a Kugelblitz black hole. Now, these are smaller mass black holes, presumably in the 100 kiloton to 10 megaton range, that are very good power supplies. Indeed, they make fusion look weak. Such black holes are believed to give off Hawking radiation, which can be easily converted into electricity, indeed far more easily than fusion. They are 100% efficient at this, whereas fusion in stars runs at 1% matter-to-energy conversion, and only for the fraction which is used from hydrogen to helium, generally only about a tenth. So matter dumped into a black hole can actually be tapped as it falls for harvesting energy much more efficiently than what is possible with stars or fusion, and what isn't converted into energy on the fall can be picked up later from the Hawking radiation. Normal mass black holes emit 100% of their mass as they evaporate, and mostly as high-energy photons, and they only seem dark when they don't have matter falling into them, radiating vast amounts of power. And only then because they just live so incredibly long that their power output is tiny, it's just a steady stream for eons. The smaller they are, the faster they evaporate. If you mastered making and feeding Kugelblitz black holes, then you probably Dyson every star you come across with cheap thin collectors and use it to make black holes, which you beam excess sunlight into, along with slowly feeding the black holes, and you make many smaller ones with lifetimes of your preference. They are sort of your ultimate battery, as they can store energy without leaking much of it, even over periods of time that make the entire history of the universe look minuscule. See our black hole playlist for discussion of that topic in details, including surviving and thriving after the death of all stars. Such a process isn't likely to be either subtle or 100% efficient either, so it is unlikely anyone is trying this approach for hiding. It is just the sort of thing that might make you harder to see than the typical Dyson swarm. Maybe you're 99% efficient at capturing mass and energy into your black holes, which would be very impressive when contemplating the mechanics of such an effort, so your Dyson sphere only looks 1% as bright as an entire star. Not really all that well hidden, being millions of times brighter than a planet still, but we could easily miss that these days. But why have a Dyson if a black hole is so much more efficient? Well, this is a key issue. You may have vast amounts of power, but you still need to radiate your waste heat. You still need to derive energy from matter initially too, which stars make a great convenient supply of, and you presumably still want your civilization all packed together, in which case it would generally pack as a sphere, emitting infrared light just like a Dyson swarm. And Dyson swarms are not dense, at least not the de facto one we usually envision building around our sun. While actual density varies by brightness, dimmer is denser, brighter more sparse, they are very spread out. I think the popular notion of a Dyson shell englobing the sun with an inverted megaplanet makes people think a Dyson would be dense, and a Dyson swarm crowded with objects and constantly at risk of collisions. In practice, it would appear more like a thin fog composed of water droplets, which would partially obscure the view of that star, and indeed the scale is about right too. It may take quadrillions of little water droplets to fog an area, and it might take a quadrillion giant O'Neill cylinders to fog up and opaque a star, but remember that these behemoths, which are kilometers or miles wide, are still spaced out in a sphere hundreds of millions of kilometers or miles in diameter and contain a volume of space over a trillion cubic kilometers or miles in size. So a quadrillion behemoth O'Neill cylinders would still each have a vast empty volume around 1,000 kilometers or miles wide all to themselves. They can always spread out wider, but they can't get more packed as a system average, or they melt, and that density goes inverse to the diameter of the spherical blob. A 10 times bigger blob can handle 100 times more heat radiation, but contains 1,000 times more volume, so 1/10 the density. And that could be a star, or a binary star, or a black hole, or 10 trillion individual fusion reactors, or Kugelblitz black holes, or some weird bit of clock tech that pumps energy from the vacuum of space, or even from another universe. Unless you have some cool way to get rid of that heat, you can only get so dense without melting. And even some process like pumping power out of a parallel universe, then pumping heat back into it, is probably missing large amounts. And if that process is 90% efficient, that just means your Dyson is 10 times denser than we'd expect, but otherwise the same. So too, you can only get so dense without collapsing in under your own gravity. As to why you would, well, if you have teleporters and transmitters that utterly ignore distance, you don't need to be close. But otherwise, every message you send and every trip you take will be slowed by having more space to cover the more spread out you are. Since something like a Dyson Sphere is already very spread out, you don't really want more elbow room, and the implication of a better power supply is that you would need that to radiate your waste heat. So basically every better power generation option just results in something that looks like a Dyson Sphere from a distance, but might seem a bit off when you double check properties like gravity, as it might be way more power emission than the apparent mass should need. Which again might trick us for a bit, but not anyone who's been in the spacefaring game for centuries, and that's why we hunt for Dyson Spheres and don't really care if it turns out artificial fusion or something better is available. Indeed, we tend to assume it is, because it wouldn't really change anything observationally. And this takes us to the question of where should we be hunting for Dyson Spheres or groups of them? And of course the basic answer is again everywhere, and presumably from the perspective that civilizations don't perpetually build more and more of them, which doesn't work well with our assumptions of how intelligent life should operate under known science. Nonetheless, if everybody builds and keeps building more and more of them, the only way we wouldn't see a universe covered in them is if by some seemingly freak coincidence folks could only start recently, like if no intelligent life had arisen to the last few million years. In the absence of that observation, we are left with the assumption that space is either empty of intelligent life that exists anywhere, or at least persisted long enough to build a Dyson, or that some flaws in our reasoning. Since we don't really lose anything by hunting for Dyson Spheres if none existed because no aliens exist, we opt to assume the latter is true for now, that we just have a flaw in our reasoning that could permit lone Dyson Spheres. If so, where to hunt? Well, again, we're looking for an anomaly of radiation, probably thermal infrared, from between just under freezing temperature to just under boiling temperature of water. That's best conducted where very little noise is present, so not in binary systems or close clusters. That would generally mean also looking mostly up or down in the galactic plane, or at a sharp angle, to minimize all the interference of tens of thousands of light years of thick galactic disk in the background. And preferably at stars where many of them in the spot are of the same age and metallicity, as that raises our odds of spotting an anomaly in absorption or emission spectra. I would say one with a nice big planet around it to help with mass measurements, but only a partial Dyson would be likely to have a planet still visible in it, either englobed later or disassembled. Essentially any places where things aren't very dense and thick, but where what is there isn't peculiar in some other obvious way that's going to make detecting other anomalies difficult. Though with the caveat that we would expect any intelligent civilization to show multiple types of anomalies that differ them from nature. The alternate path, of course, is just to hunt for all anomalies, and this is a great approach too since we would be doing it anyway. It's not like modern astronomy or finding something unusual, plops it in a drawer or gets out an eraser. So we find it, study it, and if that phenomena indicates potential or undeniable artificial aspects, there we go. What about finding groups of them? Well, that's mostly easier as your technology, and therefore your odds of noticing an anomalous large region of infrared improve, or you find that there is too much infrared present in a location compared to other frequencies, but also implies interstellar expansion was considered a good approach, and doesn't leave much of a reason why they would stop. And in the grand scheme of things, it would be pretty rare to spot a civilization that was in between their first Dyson and total galactic coverage, and this is probably about a million-year period compared to 4 billion years to get on the interstellar stage, and who knows how many eons thereafter. Tiny window but possible. There are many billions of galaxies, so many someones ought to be in that window now. And of course we have to remember we don't know if there might be constraining factors that make civilization stop growing or growing in that fashion after a few hundred stars. Maybe they inevitably discover multiverse portals and opt for faster travel to those and their endless bounty. This takes us to the last common question about hunting for Dyson Spheres, which is if we might already have found a bunch of them. What about all those voids, dark matter and stuff like that? Couldn't those be Dyson Spheres? We gave this a longer discussion in our episodes on the Fermi paradox and cosmic voids, as well as our dark matter episodes examining possible candidates. And we're running long today, so we'll keep it simple for now, and you can refer to those episodes for the detailed breakdown. The short answer is that cosmic voids really aren't that empty. They're empty like a tundra or desert is. Plenty of stuff there, but just that looks barren compared to a city or jungle. And so if those empty voids are empty because they're full of Dyson swarms and other megastructures of even grander scope, and then for some reason they left vast bits untouched, like entire galaxies, which wouldn't seem a good fit for an analogy to a nature preserve. They would also have to find a way to shut off gravity too, since those vast regions should be pulling on their neighboring superclusters if they were full of stars, which again is possible. Gravity manipulation is right up there with beating entropy on the list of accomplishments any advanced civilization should be working hard for, and unlike entropy, there are no hard physical barriers to some sort of directed gravity or anti-gravity, even if we have no clues on if or how it could be done. That still doesn't work though for voids, since again, astronomy is history, and we can see those voids in early galaxies way back at the dawn of the universe, and they've expanded more or less how we would expect based on our admittedly limited understanding of dark matter, dark energy, and early inflation. Needless to say, we might be tricking ourselves, since those are all mysteries we've been working to solve by assuming the universe is natural, and thus we might be plastering right over blatant proof of early intelligent mega-civilizations. But unless they were early forming Boltzmann brains or life from some prior iteration of the universe carrying over to ours, it would seem hard for those civilizations to have gotten up and running in the first billion years of our universe. Mind you, those other two options are on the table, Boltzmann brains and entities from earlier iterations of the universe, which is possible in multiple cosmological models. So voids are not a good fit, but they aren't entirely closed. Dark matter really is though, and for a simple reason. Its only known properties are that it interacts little, it exerts gravity, and it isn't moving faster than normal objects orbiting around a galaxy, which would be perfect for stealthy civilizations who converted their home system into a cloaked Dyson, except it's evenly spread everywhere and every when. Dark matter is very evenly spread beyond clumping near galaxies, and has been visibly so for as far back as we can look, and hasn't been growing or decreasing in quantity. So if they are Dyson spheres, we'd be talking about civilizations that have done nothing to noticeably alter the universe around them in over 13 billion years, which is possible, but is sort of like looking for a civilization of ghosts here on Earth, whose persons and properties are invisible, and who make no effort to talk to us or alter the world we can see. They might exist, but it's debatable if it even matters if they do. That's a good closing note then. On the one hand, there are no signs folks are building Dyson swarms, while on the other it would seem so logical to do so, and while our default assumption from that might be that no one is around to build them, or that building them doesn't make sense, it still does make sense to keep looking for them. Eventually we'll gather more data and maybe become a Dyson ourselves with all the resources that implies, and we can use that to continue our search while also better understanding of why and how such enormous conglomerations of megastructures get built or not. In the end, the absence of evidence is not evidence of absence, and there is still so much more for us to learn about the universe that no avenue of inquiry should be ignored, and Dysonian SETI remains one of the best options for searching for extraterrestrial intelligence that we have. So summer is here, and if you're in school or have kids in school, it is a great opportunity to forget everything you or they studied hard at to learn over the school year. The best learning is continuous learning, no multi-month breaks, just a little every day, and new material building on the old, which keeps the old fresh while adding new skills. Exercising and strengthening the mind is very like diet and physical exercise. A little every day does wonders, and just like those, it helps to have the best equipment, best plan, and best partner. And if you're looking to maintain and improve your skills in math, science, or computer science, that partner is Brilliant.org. Brilliant's visual, hands-on approach is such an effective and engaging way to learn. It makes building a daily learning habit easy. Interactive learning has been proven to be 6 times more effective than passive learning, like watching lecture videos, so Brilliant helps you learn by doing. Create programs with drag-and-drop coding, interact with charts and graphs, and play around with so many stunning visualizations. Brilliant's storyline makes even abstract ideas relatable, and beautiful interactive visualizations let you really engage with concepts so you actually understand them. Brilliant makes it easy to build a daily learning habit, and you can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/IsaacArthur or clicking on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. Incidentally, since we were talking about SETI and detecting signs of alien life today, there's inevitably the question of if there are any existing signals or signal candidates, and a couple months back my good friend Jean-Michel Gaultier released a great video quickly highlighting 8 new alien signal SETI candidates. Also, for folks wanting more on the actual astronomy and spectrum an alien Dyson Sphere might have, Matt O'Dowd over at PBS Spacetime did a great look at that a couple years back in their episode How to Find Alien Dyson Spheres. Both are great channels not only for the Fermi paradox, but space in general. And you can never have too many great shows helping explain the universe or clarify misconceptions about it. And that's what we're talking about next week as we look at common misconceptions about space, life, the universe, and everything on May 11th. After that, we'll have our Sci-Fi Sunday episode on May 14th as we explore the grim realities of super-urbanized hive worlds. Then we'll have its companion episode, Hungry Aliens, on May 18th. And in 3 weeks, on May 25th, we'll talk about how to bend space and warp reality. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.